Swayam Prabha. Digital India. Educated India.
Okay. So this is something which we want to start based on the materials which we have seen till now. What we have seen are we know something about what is a photocatalytic material, what forms you can use it. You can use it either in powder form, film form, and this is just another example. Next step higher than what we have done till now. So till now we have not used any external sources other than the stimuli light which we need for cleaning water. This is something which is based on photocatalytic material. We call it as a fuel cell. Fuel cell, the terminology comes as it describes conversion from one form of energy to another form. So we term it as a photocatalytic fuel cell because here you are going to use photocatalytic material. In what form do you use? You use them as photoelectrodes. So we have seen before how you can make it into a film form. In a similar fashion, not exactly same, but in a similar fashion, you can actually coat it on conducting substrates. Conducting substrates are something which acts like a template. So if electrons or holes are produced, these electrons can actually pass through the conducting substrate on to this external circuit. So what you do here is you have polluted water. The fuel here is the polluted water which you use. Okay. In electrochemistry, you have seen how a fuel cell works. I am not very sure if you have discussed but electrochemistry you have seen how you are already aware of what is the anode and the cathode. So here what we will be using is a photoanode. We call it as a photoanode, photocathode because it interacts with light. Okay, but these photoanode and photocathodes are actually nothing but photocatalytic materials coated on some sort of conducting substrate. You need a conducting substrate because when holes and electrons are created, these electrons should be able to flow in the external circuit. Now, many a times, instead of this photocathode, the first photocatalytic fuel cell which was reported did not use a photocathode. They used a dark cathode. What is a dark cathode? What does it mean? Dark cathode is something which will not interact with light. So the one which was reported used platinum. Okay, so it's just a metallic noble metal which is very expensive and it does not contribute to the photocatalytic mechanism which we are interested in. The only thing which was used in those days was the TiO2 based photoanode. Okay, which was TiO2, as I said, is a photocatalytic material and it was coated on some sort of conducting substrate, and when light is incident, what happens is electrons and holes are created. Okay, and these electrons flow through the external circuit. But why does it, see here we are not providing any, it is different from other photoelectrochemical cells because here we are not providing any external bias to this system. What you have is the pollutant with some electrolyte. Okay, it can be KOH, it can be sodium sulfate, it can be NaOH, some electrolyte plus the water under treatment which is called the fuel, and you have these electrodes, photoelectrodes. Other than that, you do not provide any electrical bias from outside. Then how does the electron flow in the external circuit? Because of the difference in difference in Fermi level, which is, what is the Fermi level? Are you aware of what is the Fermi level? It's better that I get one answer, otherwise I can't hear anything whatever you are saying. What is the Fermi level? That is the energy gap. See, Fermi level, that in simpler words, at absolute zero, that means if you go to 0 Kelvin, it defines a level for a material above which electrons are absent. So it is the maximum energy level which an electron can occupy at absolute zero. So this is the definition for a Fermi level at absolute zero. But definitely we do not use materials at absolute zero. It can be at room temperature, it can be at any higher temperature. So at any other temperature, Fermi level actually tells you the probability of, it is the probability where the level where the probability of occupancy of electron is half at any temperature other than 0 Kelvin. Okay. So basically any material will have its own Fermi level. In simpler terms, it's an energy level, and any two different materials will have two different Fermi levels. So when you take two different photoelectrodes, there will obviously be a difference between the Fermi levels of those two materials. The flow of electron takes place when there is and this flow is actually determined by what is the difference between the Fermi level of those two materials. Okay, that is how, in this case, you do not provide any bias, but still you have a movement of electron in the external circuit. Okay, so these are the essential requirements for a photocatalytic fuel cells. You need two different photoelectrodes, and you need the electron hole pairs to be separated. The two photoelectrodes which you use should have a difference in Fermi level, and that will determine your DOC, or the open circuit voltage. And when the electrons flow in the outer circuit, you will also be able to generate current or power. Okay, so this is a cell which can, and what is the other thing which is happening? It is generating power. Other than that, the holes which are left behind, they interact with, what do they interact with? We've seen before, no? Holes interact with water and produces hydroxyl radicals. And these hydroxyl radicals are the ones which actually degrade or clean water. Okay, these hydroxyl radicals interact with the polluted water and degrades it into lower toxic byproducts. Okay, so what you do with this photocatalytic fuel cell are two simultaneous processes. One is degradation of pollutant and the other one is generating power. Okay, so that's why photocatalytic fuel cells are a very recent addition or a modified form of PECs, where you can simultaneously produce power, energy, renewable energy, plus clean water. There are also other applications of photocatalytic fuel cells, such as you can reduce carbon dioxide, you can produce hydrogen peroxide, you can also produce hydrogen, not in this design, but there are other designs where you can have a multiple application of this type of fuel cells. Now, Fermi level, there are experimental ways of, characterizations where you can find out. There are also theoretical calculations by which you can find out what is the Fermi level of, and many of the materials you already, it is studied well and you know the Fermi level, but you can have theoretical calculations, you can find out using experimental, some other experimental techniques, what exactly can be a Fermi level of a material. Normally, I think you will be going to class 12, you will be having semiconductors now. So, you will see two types of semiconductors, intrinsic and extrinsic. Extrinsic is something where you are adding impurity to that semiconductor. Intrinsic is something which is already, it has intrinsic defects. That means you are not adding or doping it with any other impurity. These two different types of semiconductors will have different Fermi level, because you are adding more and more carriers to that, and the Fermi level will shift. So every time a particular material will depend on how many charge carriers it has, and you will be able to experimentally determine what is the Fermi level of a material. It's possible. So, yeah. See, Pete, this will be more clear when you read about semiconductors. Okay, P-type, N-type, so energy level, photoanode is normally made up of materials which will have a Fermi level. So PN, you have not studied about semiconductors now, no? As in syllabus, it's as of now you don't have. So you should know what is the semiconductor first, then there are various types of semiconductors, and then it will be more clear why you are using photocathode and photoanode. So basically in this photoanode, so what does that mean? At any room at any other temperature other than room temperature, what was the definition which I gave? The probability of occupancy of that level by electron is half. Okay, so what does that mean? You will have more and more number of electrons. The probability here is higher. It is not actually a physical level. There is no line as such which is there in a material. It is only a probability. Whenever you come to quantum mechanics or the science which we talk about now, we always talk about probability. Okay, so it is only a probability that the occupancy of this level by electrons is half. Similarly, for a photocathode, the probability lies somewhere here. Okay, because compared to this, the electrons are low in this. Okay, so that probability difference is what is determining the difference in the Fermi level. So it's not like I'm drawing a line. I mean, it's not a very correct image when you say that you have a line and you call it as a conduction band. Those are all very simpler schematic representation to make you understand, but that is not actually the case. When you go higher and higher, you'll be more clear about these. When you penetrate more into these sort of materials and study more about them.
Ma'am,
Yeah.
The holes, they react with the water in order to form the hydroxyl radicals, ma'am. But then using that, how does the cleaning process happen? The purification. How does the water get purified?
Those are reaction steps or kinetics which you can find out using LCMS analysis. Okay, there are various intermediate steps. In one of the slides I told you, so for example, if you take methylene blue, it's a very long molecule. So there are many double bonds, triple bonds in those molecules. The hydroxyl radicals comes and attacks. Attacking means it breaks the bond. It will react with that particular ring or bond, and it will break it into smaller molecular weight molecules. So that's a bigger, large molecule, and then some of the rings are specifically attacked. Attacking means it reacts with that and then breaks it into smaller molecules. So using LCMS, okay, what is called liquid chromatography mass spectroscopy study, you can actually find out the molecular weight of the products which are there. So after some time again you collect the material. So it is under treatment, you collect the water and then test it. You will see what are the products available at that time. Similarly, if you are keeping it for 2 hours, at the end of 2 hours you collect water and test it, you will see what are the byproducts then. So there are various steps through which the process happens. Ultimately, you will have byproducts. In most of the cases, it is CO2 and other non-toxic products. That is why we say that it has been degraded. It is not as toxic as it was before because you are breaking it down. Okay. So, PFCs, yes. Yeah, so dark cathode, which I had mentioned before this, dark cathode was something where platinum was used. There are other metals also which can be used, but platinum is an expensive one. The other disadvantage is if you use a dark cathode, it will not be able to absorb light in the visible range. Okay, what is the role of a photoanode here? It absorbs light in the visible range. We want a visible light photocatalytic because you can absorb 45% of the electromagnetic radiation which is incident. So instead of dark cathode, if you go for photocathode here, even that is going to absorb light, and it will also help in degradation. Besides photoanode, that will also help in degradation. So that design actually, I'll show you here, that is where you use two photocathodes. This is called a double chamber, double or dual photoelectrode system. That means instead of keeping a one tank or one chamber, you have two different chambers where you can use two different photoelectrodes. One is a photocathode, other one is a photoanode. In between you see something here is what is called this is a membrane, normally Raphon membrane which is used, which will allow hydroxyl ions which are generated on this side to pass on to the other side. So the advantage of this type of design is that you can use two different pollutants to be degraded in two different chambers. Also, you can also use this under anaerobic conditions, that is in absence of oxygen. It will also be able to generate hydrogen in the second chamber, that at the photocathode. Okay, so as I said earlier, PFCs are not only used for cleaning water, they can be used for multiple purposes. You can functionalize them as per your need. You can use them for CO2 reduction, for H2O2 production, hydrogen production, and obviously cleaning water. So this is one type which is called dual chamber, dual photoelectrode. The previous one which we saw was a single chamber, single photoelectrode, or single chamber, dual photoelectrode. So instead of dark cathode, if you are using both photocathode and photoanode, it's a, you have a question again? Yeah, you can see films and dialysis bags were only cleaning water. Only in the cleaning process. Here you are, besides cleaning process, you are doing many other things. So obviously you will go for a system which has multiple applications at the same time, no? If somebody is giving you chocolate and orange, okay, if you dislike orange, it's a different thing, but if somebody gives you Cadbury and Ferrero Rocher, you want to take both, and you'll take only one. If there is an option of taking both, unless and until you are allergic to one of those. So we always look forward to mechanisms where you can achieve multiple things. So you are producing renewable energy. Hydrogen is a very sought after renewable energy sources now. So obviously you will go for processes not just for cleaning water, where you can use a polluted water. You are not using normally for producing hydrogen. What is a very common method which is used for producing hydrogen? Electrolysis. So electrolysis, if you are aware, means clean water. You are not using clean water here. For cleaning that water to produce electrolysis, you will need to provide some resources. Here you are not doing that. You are just using the polluted water to produce hydrogen. I have not shown that mechanism here, but you can use wastewater to produce hydrogen. Okay, so that is why this is very much advantageous over the previous processes. Not just in cleaning water, the first two were, all the three processes using powders or films or these are off-grid processes. That means you are not providing any energy. You can do it anywhere, just the source which you need is the sunlight. That's all. These are all off-grid processes. No external electrical bias is needed. Yeah. Switch it on.
Ma'am, so the photocatalytic fuel cell, can it be implemented at a large scale system?
It can be implemented, and then works are, it's still at a research stage. It has been scaled up, but not in the industry still now. So these are all at research level as of now. But it can be done. It can be used in what are called batch type reactors which are currently being used in water treatment application. I mean, if you go to any water treatment center, you will have batch type reactors also. So these can be implemented there.
Yes, ma'am. Thank you, ma'am.
Ma'am, there's a membrane in between the two chambers in the dual chamber, ma'am. Does it have a similar function to a salt bridge in an electrolytic cell?
Not similar one. Here, see, you need, because you're in this one, in this system you can have two different pollutants, but even to degrade those two pollutants, you are using non-selective hydroxyl radicals. So, you cannot have hydroxyl radical production here. So it's only being produced at photoanode. Okay. So, but you still want it to come to this side and degrade the pollutant. So you need a membrane to allow these ions.
So it's only unidirectional, ma'am.
Yes.
Thank you.
These kind of like ideas, how long have they been around? Like how long have they been researched for?
How long?
Have they been researched for? You said they are still in the research stages.
Yes, because these are modified forms of PEC. See, PEC is something photoelectrochemical cells have been in use for many years now. But photocatalytic fuel cells have been, I think, maybe 6-7 years now. But to scale it up, you need many other things to be optimized. It's not like you can do it at a local scale. Okay, but to scale it up, you just don't need research. There are many other things which are there. Okay.
So this one you said that the hydroxyl ions can only move in one direction, right? In this two chamber cell. So my question is like, if we use photocathode and photoanode, both are like photocatalysts, then why isn't it possible that there itself it can be produced and the reactions can take place, right? The sunlight can fall on the photocatalyst, there itself a hydroxyl ion can be produced, and there the cleaning process can take place, right? So in that case, why is the membrane needed? Like,
see, photocathode, the reactions at photoanode are different from those what are happening at photocathode. Photocathode does not produce hydroxyl radical. Okay, you have hydroxyl radical forms because you have holes left behind here, absence of electrons, which react with water and produces hydroxyl radicals. That is produced only in the photoanode chamber. But you need it to come to this side to clean water. So there is a membrane. It's something like a path. You are giving a path for it to move forward to the other chamber. Hydroxyl radicals are not produced in the photocathode region. There the see, these electrons actually come here and they react. If it's an aerobic condition, they react with oxygen here and produces superoxide radicals. Only superoxide radicals take part in degradation here. But we need hydroxyl because they are more efficient and they have as we know, they are non-selective in nature. So we want to use hydroxyl radicals also. That's why you need to have and also to complete the circuit.
thank you.
Okay, so this one, I'll skip this slide. It just shows that you have if you use some processes like PFCs, you can address many things. Many of the goals which are addressed in or put forward in SDGs related to water pollution, energy demand, water footprint, carbon footprint. Okay, you are not using any other source of energy, you are producing energy, you are producing hydrogen. So all these can be taken care of if you have specific processes which can be scaled up like those of PFCs. Okay, so this was all about the processes, and in the next one, yeah.
For the powder that is coated, it still has to be manufactured and replaced at a regular intervals, right? It's not.
Can be recycled, but it cannot be recycled infinitely. It has to be just like when you go for a RO system, your candle has to be replaced after some. So in a similar fashion, here again it has to be done. Okay. Okay, so we were discussing about functional materials. Now specifically, I would like to take you to one class of materials which you have heard of, I think since the last decade, and those are the nanomaterials. So I hope many of you are aware of what is a nanomaterial. We will look into why nanomaterials are functional materials and what are nanomaterials. Okay. These are again just as we know, for our applications we can design these nanomaterials into specific materials so that you can use them for some specific applications. So before going into the nanomaterials as such, I would like you to have an idea about what exactly, whether it's a new thing which is there or which was already there and we didn't know about what is a nanomaterial. So I don't know how many of you have seen this movie. It's not a very new movie. It's I think 1997. What was there? The content, you remember the content of this movie? Yeah.
The scientist was trying to find a shape materials. He tried to somehow
Accidentally, yeah. So the scientist accidentally shrunk his own kids, I suppose, and his friends. And so the kids, after they find themselves in a new environment, so they are in a much smaller scale now, and then they can see new things which we cannot see. So if they are at that scale, they can see the environment now. Obviously, we are not able to see, even though it exists. So what I want to say from this is nanomaterials are nothing new. It was already there in nature, unless and until it's a synthetically designed one. Nanomaterials were already existing in nature. The only problem was we were not able to see those nanomaterials. So right from 5th century BC, we have had existence or proof of existence. It may have existed before that. We have proof of existence of nanomaterials since 5th century BC. Now, only when we could see those, we believed that the existence of nanomaterials. Now, why is it such a buzzword? Because when you make any material into a nano form, the properties completely change. So that is what we are going to see. Why does it change? So what exactly is a nanometer? 10 to the power of minus 9 meters. So, but 10 to the power of minus 9 meter, any dimension, for example, if you take this water bottle, can you write the dimension of this or the length of this in nanometers, in terms of nanometers? It's possible, right? So this can be some thousands of nanometers, but whether is it really a nanomaterial? No. So why can't I call it as if it's 1,000 nanometer material, I still call it as a nanometer, then why is it not a nanomaterial? Scientific notation? 10 to the power of minus 9 meter is also a scientific notation. Doesn't have the properties? What are those specific properties?
they have like different colors. Depending on their size.
All nanomaterials have different colors? No, it's good that actually at least whatever you have heard of, you can recollect something from there. Yes?
Because each particle should be a nano size, which it might not be a nano size, that particle.
Each particle has to be a nano size. Even the particle inside this, I can write it into a nanometer scale. See, if I break it down, let's say I come to one atom, I can write that dimension also as nanomaterial. This also can be a nanomaterial. I mean, in terms of nanometers. Okay.
Say nanoparticles can be surfaces which are 1 or 2 atoms.
surfaces which are no, that is, you're telling me a definition of nanomaterial. But what I'm saying is, how is it different from that? Your 1 or 2 atom thickness is also expressed in nanometers, few nanometers. This is 1000 nanometers. So how does it, why is it different? As she said, the properties are different. Okay, that is one way of saying that. I want to tell, yeah. You see, that is why this slide, seeing is believing. So only if you see, you will believe. Is that the case? Even if you are not able to see, it is there. So we derived or we invented techniques for seeing them and then started believing. That doesn't matter. Yeah.